Good morning, everyone.
Good morning.
Good morning.
Yeah, now today we are going to look at the pattern or the properties that you require in a radiator, an efficient radiator, so to speak. And I hope everyone can see my document that I'm sharing. That is antenna properties. Is it okay, everyone? Can you see it?
Yes.
Yeah. So what we said is that when we are creating antennas, we want to radiate as efficiently as possible. That is, all the power that you feed to the antenna as a load will be launched into the sky for it to go to the intended direction of the intended recipient. And therefore, all we can say is that when we saw that for the Hertzian dipole or the magnetic dipole, we saw that the radiation was almost equally, not equally, it was always, it had a perfect kind of radiation pattern, which we say that in the E plane, we have the electric field being radiated as a, as a figure 8 or a donut kind of shape, while on the horizontal plane, of course, it's circular, and the vertical plane for a vertically oriented dipole, we saw that it was a figure 8. And we saw that the opposite, the same thing was the same for the horizontal magnetic dipole, where the field in the vertical plane was the H field, which was figure 8, and circular in the horizontal plane. Now, no physical antenna will radiate isotropically, that is equally in all directions, and there will be a direction in which the antenna radiates more efficiently. So a plot of the relative far field intensity against the direction at a fixed distance from the antenna is what is referred to as the antenna radiation property or pattern. So the radiation is usually a 3D plot of the normalized field intensities. That is, we are normalizing them with respect to the maximum radiated electric field or magnetic field as a function of both the elevation angle theta and the azimuthal angle phi in the 3D or spherical coordinate system. And however, it is usually usual to plot the pattern in a 2D plot, that is in a graph, in a two-dimensional graph, in two of the principal planes being, that is, we'll plot the fields against the elevation angle theta at a fixed angle phi, usually taken as the phi equal to 0 degrees, that is flash with the x whatever, x plane, xz plane, or we will take it as 90 degrees. And this is usually called the E-plane pattern, or what will be referred to as the theta plot. So if you are going to be using the software packages to design antennas such as, say, HFSS or the CST Studio, you will find that they'll always be referring to them as E-plane or either the theta plot, so to speak, for the phi equal to 0 degrees and 90 degrees, and we are plotting against theta. And then we could also plot against phi at a fixed theta, and we saw that for the thin wire antennas, the theta equal to 90 was the direction of the maximum radiation of the electric field. And this it's usually called the H plane or the 5 plot. So in some cases, the normalized field distributions will then be plotted, and the patterns will then be labeled as the measured plots. That is, you are giving the absolute field radiations. Otherwise, the others that we've been talking about here, the normalized ones, usually the quantities have no dimensions because we are already normalizing them to the maximum value. But they won't look very different. It's only that this will have meters per volts per meter or amps per meter and so forth. So we recall that for the vertical Hertzian dipole, the far field magnetic and electric field intensities were given by h phi equal to the j, where j is of course the complex number operator or variable, that is root minus 1, multiplied by the current element divided by 4 pi and divided by the radius r from where the distance r from the dipole, and multiplied by the propagation constant k, the sine of theta, and the phase propagation constant, which we show was just that of the plane wave that we are calling the exponent of minus j k r. And theta, E theta, of course, was given as the the curl of that h phi, that is z cross the h phi there, and multiplied by eta, and therefore we have a current element there multiplied divided by 4 pi r, and then multiplied by eta, which is the intrinsic impedance of the medium in which the antenna is immersed, and multiplied by the propagation constant, and of course the sine theta exponent of minus j k r. I've written it in this form so that we can see all we are doing is to multiply h theta by eta to get the value of e theta there. And normalizing the field intensities to unity, we then obtain that h phi is just going to be given by that value there, and e theta n is given by sine theta. So we note that h theta is, or e theta is going to be independent of phi, and will vary with theta as sine theta, which is the E-plane pattern function for the Hertzian dipole. And because we are taking the values of the modulus, we shall see that we'll have two circles for both directions. So at any angle phi, the sine theta, the modulus, will describe two circles of unit radius on either side of the dipole, symmetrically placed above the dipole. And the H pattern is a circle with a center above the vertical dipole, since at any distance r from the dipole, the E theta normalized is going to be equal to unity, because we are just saying it's a function of sine of theta, and therefore at theta equal to pi by 2. And the patterns are, however, more complicated with when we look at practical antennas, because the practical antennas will have certain issues. That is, we have talked about infinitely thin or infinitesimally thin wires, that is filamentary currents. We have talked about very short lengths, but we'll see that for practical antennas, the lengths will become of course, of a comparable magnitude with the wavelength of the signal. And therefore, this will introduce other issues into the patterns, and we shall see that the practical patterns will not have this kind of pure looking patterns. So we show that the illustration for the E and H plane patterns of a vertical Hertzian dipole, and what we have is, that is, the dipole is somewhere in between here. That is a dark thing. It's not being seen well. Maybe I should change the color. And we see that the minus 3 dB points for that beam is very wide. It's about 90 degrees between the minus 3 dB at the top and the minus 3 dB at the bottom there. And if we look at the dipole looking from positive infinity and looking down the dipole, we'll see the dipole is at the center, and the H pattern is actually a circle at the angle theta equal to pi by 2 or 90 degrees. So that's how the patterns will look. And therefore, once we start looking at the lengths, that is dipole lengths, that are different from this, all we shall see is that we shall get a similar kind of pattern, but it will be distorted, and we may even start getting other lobes that are not maximum, and this will call them side lobes, and we shall see this as we go along. So if the H pattern is plotted against phi with H theta, with E theta normalized in general, the pattern will exhibit one, a region of maximum radiation between the first null points around it, and this will be called the main lobe. So regions of minor maxima will be called the minor or side lobes, and we can show an example of a case where, say, for example, we put a very long antenna, and therefore we get a backward lobe, which is a maximum one. In many cases, you don't want this to happen, and therefore there will be a figure of merit or a performance figure, which will be the ratio of the forward lobe to the backward lobe, called the front to back ratio. And this is very important. The side lobes are these ones which we are calling the minor lobes, and they may have smaller values or even bigger values. So the first null points are, of course, these regions where the field becomes zero, and this will be called the first null point. You can get a second null point, third null point, and so forth. Okay, this is like an interference kind of pattern, so to speak. It's called infringement pattern. Now, sometimes you don't plot it in a polar plot, and you can plot it in a rectangular coordinate as shown here. So all you have done is to just cut through around the theta direction, and we are plotting against phi. And what you'll get is that we'll get similar expression like what you got for the psi function in your Fourier transforms of a square wave, so to speak, or a square pulse. This is how it would look like, or what we usually call the Mexican hat if we were to look at it in 3D. So for comparing radiation patterns of different antennas, the important pattern properties that will include, one, the width of the main lobe, which can be specified as the angle between the half power points, that is the minor 10 dB points, or between the first nulls, given the symbol BWFN. Okay, that is bandwidth between first nulls, or half power bandwidth. Or you could take the minus 10 dB points rather than the minus 3 dB. This is the minus 3 dB point, so to be. Then there is another one which we call the level of the side lobes relative to the main lobe or the beam. Remember, the main lobe is the desired lobe. That is, you want to direct all your power in that direction. But when you have side lobes, it means that some of the power is leaking to other directions that are not desired. And some of these directions may have reflector or obstacles, and this may cause reflection patterns which will mess up how your pattern looks like. Say, for example, in the new 5G NR or new radio platform, we want to direct the lobes or the power to the given device, not to all other devices. That is, select a device is selected and it's sent all the power. And therefore, the main lobe, we should have very few low side lobes because other devices should not receive that power. So in modern antennas, this is sometimes specified as the first minor lobes, and they must be greater than 40 dB below the main lobe for a good antenna. So another parameter is, of course, the location of the side lobes, which may be specified in some cases. So the beam width specifies how sharply the antenna is able to concentrate the radiated power. It's more like, if you look at it in the optical sense, it's like when you have a lens. Say, for example, when you are looking at an object, the object, of course, you are trying to focus the light that is reflected from the object through your eye to go to the antenna. If you want to actually see the details of that particular object, there's a point in the eye at the retina called the fovea, and the fovea is a small spot, and you want that light to be focused on that small sensitive part for you to see the details more sharply. Okay, and therefore all we are saying is that the antenna may not be able to sharply send the power in the given direction, and it will be broad, so to speak. And this will usually be specified by the antenna directivity. Now, the beam width does not provide information on other parameters such as the lobe levels or their locations. They could be located very close to the main lobe, which could be a problem, or they could be located nicely but far away from the side lobe, from the main lobe. Or they could have a level that is below the 40 dB we were talking about, or above that, which is not a good thing. But the beam width will just tell you how sharp the main lobe is. So antenna directivity, or a directive gain, is usually given the symbol GD, theta, and phi. It's a function of the elevation angle and the azimuthal angle, and it's a measure of the ability of an antenna to concentrate radiated power in the given direction. So directive gain is defined in terms of the radiation intensity K, theta, and phi, which we already looked at the last time, and defined as the average radiated power per unit solid angle. And I hope we all remember how we described the solid angle, or how we define the solid angle. So each r squared surface area of a spherical surface of radius r will subtend a unit solid angle at the center of the sphere. And therefore, we can see that K, theta, phi is just going to be given by the radius of the sphere squared and multiplied by the average pointing vector of that antenna. So time average power radiated over a closed surface S and enclosing the radiator is usually given by PR equal to the integral over S of the time average pointing vector over that distance and that surface, and equal to, therefore, the integral over the solid angle of the surface and K theta phi, that is the radiation intensity, and multiplied by the element of solid angle. And this, we see that the solid angle is just defined as sine theta and multiplied by d theta and d phi, so that r squared d omega, or the element of solid angle, is the same as the d of S, that is the element of surface area. And therefore, the directive gain will therefore be given as GD, theta and phi equal to K, theta and phi, and divided by the radiated power, the average radiated power divided by the solid angle, the total solid angle of a sphere, and this is given by 4 pi K theta phi by the integral that we have up here. Remember, we are saying that we form the S, or the spherical surface, centered at the radiator itself. And therefore, directive gain is the ratio of the radiation intensity in a given direction theta phi to the average radiation intensity, when we assume that the average radiated power is radiated isotropically. That is, we could treat the sun as a radiator or a point source, which is radiating equally in all directions, but the only direction of interest that we are interested in, say for example, if we are designing a solar panel, a solar power system, the only useful radiation from the sun is what will be coming in the direction of your solar panel. And that's why for those of us who will be doing power electronics, we'll be talking about maximum power tracking and so forth as you make solar powered supply systems. So the maximum directive gain is usually defined as the directivity of the antenna. And the directivity will therefore be the ratio of the radiation intensity in a given direction. That is the direction of maximum radiation to the average radiation intensity. That is, you are going to get a value of theta and phi that are representing the direction of maximum radiation. And then we'll define that as K max and divide it by K average. And the directive gain is usually given, or the directivity of the antenna is given the symbol D, and it will be given by the GD max, okay, in that direction as K max divided by K average. And we see that this is just 4 pi K max over PR, where we are saying this is the average radiated power over the whole surface. And this, we can therefore give it in terms of the fields, And we see that it's going to be given by the maximum, the magnitude of the maximum electric field squared and divided by the integral over the solid angle, which we have now defined it in the theta direction and in the phi direction, and that will be given by sine theta, d theta, and d phi. So directivity is usually specified in dB scale, referred to unity, but may also be defined or specified relative to an isotropic radiator that is given the value dBi. An isotropic radiator is a point source that radiates power equally in all directions, and therefore it will have a directivity of 0. And therefore, when we compare our antennas, we will always be comparing them in terms of the directivity and in values or units of dBi. But remember, dB is not it has no units, that is, it has no dimensions, but it's just a good number to work with. So we know that for the Hertzian dipole, therefore, we had a Poynting's vector, a time average Poynting's vector that was given by that equation there, where we found that it was just going to be given by the magnitude of the E theta squared and divided by eta, that is the intrinsic impedance, intrinsic impedance of the medium. And thus, for the Hertzian dipole, you can see that K is just going to be given by a half the element, that is the current element, divided by 4 pi all squared eta K squared and sine theta, where this is of course what we have, this value here of the squared, and then we are divided with the eta, and the eta that we had there squared is reduced to just a single eta there. And therefore the directive gain for this radiator will therefore be given as the GD theta and phi equal to 4 pi multiplied by the sine squared theta over the integral of the bottom, that is the average power radiated over the whole surface. And this will give us a value of 3/2 sine squared theta. The directivity will then be given as in the direction of maximum radiation, which we saw that the maximum radiation is for theta equal to 90 degrees, and therefore we see that it's going to be given by GD pi/2 of phi, which is equal to 1.5, and this is about 1.76 dBi or dB with respect to the isotropic radiator. So antenna efficiency, I hope we are able to solve this problem. That is, you can always use integration by parts, okay, to integrate this value here. We see that this is sine squared theta and sine theta, okay. We can change this into 1 minus cos squared theta and multiply by sine theta, and then we can already see integrate that quite easily, because we'll get a sine theta multiplied by cos theta squared, and you can see that it will be immediately seen as 3/2 sine theta squared, or 2/3 sine cubed, whatever. And when we add these values in, we'll get the correct value there. So antenna efficiency is specified through the power gain, which is given as dP relative to an isotropic radiator. And remember, I'm sure all of us are conversant with power gain from electronics. An antenna is basically a passive element, and therefore by gain, we are not talking about addition of power. All we are saying is that we are borrowing some of the power that was to be radiated in different directions. If it was radiating in all directions equally, all we do is to borrow that power that was being radiated to other directions and concentrating it in one direction. That's why it gives us we are calling it a power gain, but it's not an addition of power, so to speak. Okay? So by definition, GP will be the ratio of the maximum radiation intensity of an antenna to the radiation intensity that would result had all this power been radiated isotropically. And ohmic losses in the antenna and nearby conductive structures will make the radiated power PR of an antenna to be lower than the input, that is the electrical power input, or the excitation power, which is just PI. And therefore, we can write that the input power to the antenna will be equal to the sum of the power lost, that is the power load dissipated in the antenna system, plus the radiated power. And therefore, the gain, that is the power gain GP, just going to be given by 4 pi K max over PI. The radiation efficiency of the antenna is then the ratio of the power gain to the directivity, or we can write it as the eta R, the efficiency for the radiation efficiency, equal to the power gain divided by the directivity of the antenna, or PR over PI, which gives us a value of PR over PR plus PL, or 1 over 1 plus PL over PI. So when constructed antennas will have efficiencies that approach 100% in general. So a measure of the radiated power from an antenna is then called the radiation resistance. If you recall what we said, is that it's an equivalent electrical resistance that would dissipate the same power as the radiated power of the antenna if it was carrying the maximum current. Okay, that is the amplitude current of the antenna that is exciting the antenna. And this, we say that it was an equivalent resistance that would dissipate PR with the same current flowing through it. So for the Hertzian dipole, we have that PR is given by that expression there. And this we can see is what I was alluding to. We just have an integral of sine cube theta with theta d phi. Or in other words, we can get a value of that nature, and we get that this is going to be given by a half I squared, that is, we are borrowing out the amplitude of the current and divided by a half, then we multiply that one by 80 pi squared over L by lambda all squared. And this is equal to a half I squared and R. And therefore, by comparison, we can always see that this value here, remember we have substituted the intrinsic impedance of free space, which is 120 pi. That's where the 40 is coming from, or the 80 is coming from, because we are going to divide by a half. And therefore, we get a value of 80 pi squared L by lambda all squared. And now we see what we were talking about before. For the Hertzian dipole, we say that L was much smaller than the wavelength of the signal. And therefore, we can see its radiation resistance will be very small because L by lambda is very small. So for this to hold, we must then have that L is much smaller than lambda, however, and for the assumed uniform current distribution to hold. So an example, an isolated Hertzian dipole is made of a conducting wire, radius A, length L much smaller than lambda, and a conductivity sigma. Determine the radiation efficiency of the dipole. So we let the amplitude of the current be I, and the wire to have a loss resistance that we call RL. So ohmic losses in the wire will therefore be given by PL equals to a half of I squared RL. So the radiated power is given by PR equals to a half I squared and multiplied by the radiation resistance RR. And for this wire, we have that RL is given by the surface impedance from the skin effect multiplied by L, that is the length of the dipole, divided by the surface area of that value. And we get an L by twice pi A and root of pi F mu C by sigma C, where the mu C is the magnetic permeability of the conductor material. So the current has been assumed to be the same all through, that is to be uniformly distributed over the wire. And hence, the power loss over the radiation loss, the radiation power is going to be given by the loss resistance divided by the radiation resistance, and we get a value of that nature, which we can say that is going to be given by lambda by L squared over 1 over 80 pi squared at the bottom, and we get a value of, and the efficiency is therefore going to be given by the reciprocal of 1 plus Rm over 160 pi cubed L by A, that is the ratio between the length and the area and the radius of the wire, and multiplied by the ratio or the reciprocal of the length to wavelength ratio of that antenna. So for example, if we were to take a dipole made of copper wire with a length of 2 meters and a cross section of 2.5 millimeters square, and we operate it at 1.5 megahertz. And for those of us who are here, we can try to see whether the 1.5 megahertz, the 2 meter length of antenna is much larger than the lambda. And we do quickly that, we can see, of course, I've done it here. We see that the lambda, the wavelength of the signal, is 200 meters. The Rm is going to be given by 3.2 times 10 raised to minus 4 ohms, or 0.32 milliohms per square. And therefore, the loss resistance is just going to be given by 0.114 ohms, and the radiation resistance is just 0.079 ohms. And therefore, when an antenna is driven, is operated at a wavelength such that its length is much, much smaller than that wavelength, the radiation resistance is going to be very small, and therefore we can see that even the directivity of that antenna is going to be poor, and the radiated power is going to be very low. Therefore, such antennas are usually very inefficient radiators. So we can see that eta R is approximately 41%. And that brings us to the end of that part of the values. So I'm open for some questions before we continue to the rest, to the next topic. Any questions so far? Note, at this particular level, all we are required to know is about antennas and their radiation. So we are just introducing the antennas. We'll have a proper treatment of all the different kinds of antennas, including the reflector antennas, when you get to the 5th year in the light current option. So any question?
No question.
Okay, fine. So in the interest of time, then I'll continue and I'll go to the next part, which is what I was referring to as the antenna arrays. Just like we have seen like a Fourier series expansion of square waves, or square rectangular pulse strings and so forth, can be used to describe, or not even just square waves, that is, Fourier series can be used to describe any periodic function into sinusoidal functions, okay? Or we use the Fourier transform for the energy waves. It's possible for us to be able to describe this as in terms of the sinusoidal, as a superposition of sinusoids. So the same thing is that we can always use the knowledge obtained from treatment of elemental antennas, that is the Hertzian dipole and the magnetic loop, okay, to analyze antennas for which the length of the antenna is much larger or is of the same order of magnitude as the wavelength of the signal, and we use superposition of the small contributions of the small little elements of current that will have divided that length into. So an antenna array is a group of similar antennas that is arranged in space and excited in a prescribed way to optimize the desired characteristics of the radiation. One, the most important being the directivity. We want to maximize the directivity of that particular antenna system. And two, we may want to minimize the back to front lobe, whatever radiation ratio. So we often seek to, one, maximize the antenna directivity while minimizing the any side lobe levels that the side lobes levels for any side lobes that will be generated in the radiation pattern, especially in wireless communication antennas. Two, we want to improve the radiation efficiency and spatial coverage in a broadcast application. Say, for example, for a radio station, you don't want to direct that power in just one given direction because the people receiving your radio signal will be distributed all over, not always equally in all directions, but they will be distributed all over and you want to reach them all through. And therefore, for a communication radio, say for example, for a cell phone, so to speak, the antenna should be able to cover the cell area. You know that usually the communication or the regions are usually divided into hexagonal cells, and with an antenna covering only one cell, one antenna covering a cell, and any overlaps, of course, will be dealt with by other antennas in the next cell, so to speak. So the far field intensity of an array is usually defined as the vector sum of the contributions to all the radiating elements in the array at the given field point. And the spatial arrangement of the array element can take any geometrical form. That is, we could arrange the elements into linear arrangement of array elements along a straight line. This can be called the axis of the array, or linear arrays. Then we can have a square or rectangular or any polygonal arrangement to form a 2D array. So for example, a reflector, a dish reflector that we have can be treated as an array when we introduce the concept that the power or the radiated energy is the reflected energies can be treated as being radiated by small elements of surface over the whole reflector, and therefore it will form an array there. So these square or rectangular ones, this is how if you have conversant with a MIMO system that will be used with a 5G communication system, most of them will be arranged in a square or rectangular array form, and to maximize or to do what we call beam forming. You could also have a 3D array, okay, in all that is, you can have it in cuboid form and so forth. So these are just not exhaustive, but just an example of the different shapes that you can have. As this is an introductory topic, therefore, we are going to just confine ourselves in the study or in the treatment of linear arrays, where we have the radiating elements arranged along a straight line, which we will call the axis of that array. So, a two-element array then. So this is the beginning point where we have two similar elements or antenna elements, okay, that are assumed to be point sources, and therefore they should be radiating isotropically in all directions. That is, they are radiating the same power in all directions. That is, there is no directivity there. That is, we have a directivity of unity. And we are spacing them at a distance d between their axes, so their centers, so to speak. So the elements will then be assumed to be spaced at a separation d and excited by equal amplitude currents, but with the current in an element 1 leading by an angle phi. That is, it's leading the current in element 1, in element 0 by a current angle, by an angle alpha. So we have the element 0 and the element 1. So the current here and the current here has the same amplitude, but the face of this is ahead of the face of that one. This distance d is the separation distance, and we can see that we are looking at a field point P that is sufficiently far away from the axis of the antenna array such that R0 and R1 can be assumed to be almost parallel as we arrive there. That is, R0 and R1 are very much larger than the separation D. And therefore, we can make this kind of assumption that R0 will be approximately larger than R1 by a value D sine theta cos phi. So the far field electric field at P of each element will then be assumed to be in the theta direction and given by the value E0, that is for the first element, is given by EM, that is the maximum or the amplitude of the E field multiplied by the element factor and multiplied by the propagation factor. And E1 is going to be given by EM multiplied by the same antenna function, pattern function, because they are identical, so we have the same f theta phi, and multiplied by the propagation factor for that particular value, and multiplied by the phase angle of the current exciting the second element. And here we understand that EM is the amplitude of the electric field intensity, and f theta phi is then the element pattern function. The element pattern that is for the particular antenna. Say, for example, if we are dealing with the Hertzian dipole, then we'll have a f theta phi of sine theta that is just equal to sine theta, so to speak. And therefore, the total field at P is going to be the contribution of the first antenna, that is the electric field contributed by the first antenna, and the added to the contribution from the second antenna. And once we do that, we just get the values, we bracket them out, and therefore we have the propagation factors coming in, and this delayed by an exponent of J alpha. So if R0 and R1 are much larger than D by 2, then in the denominators, we can always make the approximation that the two radii, the two distances are not different. That is, they are almost parallel at P. In the phase factor, however, just like we did before, the difference between R1 and R0 is very important because of the propagation constant that we have there. The propagation constant can be very large, so that when we multiply K delta R, it can be a very large, a very large electric length, so to speak, or significant. So with the assumption made about the distance of the field point from the center of the array, then we can have that R, the vector R0, and the vector R1 will therefore be almost parallel. So from the geometry shown, we can write that R1 is approximately R0 minus D sine theta and cos phi. And if we were to do this, that is where we have displaced, or we have rotated our function a little bit so that we have the y direction and the x direction. So all we are talking about is that we are looking at the field point pi, and we are looking at that value there. So hence, when we do the addition, this is what we are going to get. We are going to get, that is, we'll take the first value out, that is factor it out, then we just have 1 plus the exponent of j multiplied by kd sine theta cos phi plus alpha as the phase of that particular value. And when we add those two together, we'll get a value of that nature. That is, we get a value psi by 2, exponent of j psi by 2 multiplied by 2 cos psi by 2, where the psi is now defined as the kd, that is the phase delay because of the separation, multiplied by the sine theta and the cosine of phi plus alpha. The magnitude of the far field, electric field intensity, is therefore going to be given by the modulus of this value here. And we can see that all those j's will go to 0, and all we are left with will be just the magnitude of the cos phi by 2. We'll have the factor, that is the pattern factor for the element, and multiplied by twice the amplitude of the field, and divided by r naught, that is the distance to the field point. So we may understand these factors in the expression as follows. We have a spatial delay of the field with distance from the axis of the array, and this will be given by A twice EM divided by R naught. That is, the electric field at the field point will be attenuated by the distance from the array point. That is, the E field is decaying as 1 over distance from the antenna axis. 2, we have the element factor, that is for the radiating element, which is the magnitude of f theta phi. Then we have a normalized array factor. The array factor is now the introduction, the contribution, or the shaping of the radiation pattern of the antenna system appearing because of having more than one radiating element in that system. And this we can see for the 2-element radiator or antenna system. We have that the normalized array factor is just a cosine of psi and divided by 2. And this is then a principle, an illustration of what we call the principle of pattern multiplication. And this is very important principle, which you are going to find very useful when you start designing antennas or antenna arrays, or any other type of antenna that has comparable dimensions to the wavelength. Okay, when you get to the 5th year, or when you get a final year project that requires you to design antennas, you should always know that this is a friendly principle for you. So as an example of this application, we are going to consider a 2-element array of vertical lambda by 2 dipoles, okay, oriented in the z direction with a separation d between them. So the far field, electric field, can then be written immediately that we have the array pattern, okay, normalized array pattern factor, multiplied by the pattern we got already obtained when we were dealing with thin antennas, which was cosine of pi by 2 cos theta over sine theta, where we are using the maximum direction, that is when theta is in the direction of whatever, at the maximum level. And then we have the value of that is okay, for KL, which is K multiplied by lambda by 2, we'll see that it will be 90 degrees, and therefore the cos KL will disappear, and therefore we are just left with these values of thetas multiplied by that amplitude factor that we have already seen before. So in this case, the psi will be a function of theta as well, and will therefore not be the same as in the individual dipoles, except only when theta is equal to pi by 2. In the H-plane, theta equal to pi by 2, and the array factor will determine, okay, the array radiation pattern. So, an example, you are required to sketch the H-plane radiation patterns of a 2-element array of 2 identical parallel dipoles for d equal to lambda by 2 and alpha equal to 0. That is, they are being fed by a co-phase, in-phase currents, and d equal to quarter by 4, that is lambda by 4, and a delay of minus 90 degrees. So The dipoles are going to be assumed to be oriented in the z direction as shown and arranged along the x-axis. So in the H-plane, we have that theta is equal to pi by 2, and therefore each dipole will then be omnidirectional. Omnidirectional means that it radiates equally in all directions around a circular surface. So the normalized pattern function is hence going to be given by equal to the array factor, and therefore you can get that if psi is going to be cosine of psi by 2, which is equal to the cosine of a half pi d cosine phi plus alpha. And for d equal to lambda by 2 and alpha equal to 0, you can see that the array factor is just given by that equation there, and we get a value of cosine of pi by 2 cos phi. Or in other words, it's going to be 0 in the direction phi equal to 0 and pi, and it's going to be unity in the direction of pi by 2. This can be seen because if we put pi by 2, this will be the magnitude of cosine of pi by 2, and therefore that is going to be unity. Pi of 0, that is cosine of 0, and that will be unity. If we put phi equal to 0, this is going to be unity, and therefore it will be cos pi by 2. If we put pi here, it will be the cosine of the minus, or the cosine of minus pi by 2, which are both equal to 0. So, and this is usually called the broadside array pattern because it's radiating along the axis of the antenna. We have the radiation pattern will be having a null. It will be 0 along the array axis, but it will be maximum at 90 degrees to the array, and it will be a given value, okay, so as phi changes from 0 to pi above the axis itself. And therefore, we call it a broadside array pattern because if you are to assume that it's a ship, you know, long ago, the days of the buccaneers and the like, that is the pirates, you had ships that had cannons that were arranged along the side, the long side of the ship. And therefore, for you to attack the coastline, you needed to orient your ship parallel to the coastline so that your cannons can be directed towards the coastline. Okay, and therefore, since we are saying that we are on the broad side of the ship itself, and therefore our array is radiating in a direction that is normal or perpendicular to the axis of the array itself. So the radiation pattern will have a form of that nature, that is a figure 8 kind of radiation pattern, that is above and below the array axis. The axis of the array will have the radiation, and it will be maximum when in the normal direction to the array. So when d is equal to a quarter lambda and alpha is minus 90 degrees, we'll then have that we can see that phi is going to be given by those values there, and we see that it's just going to be given by the cosine of pi by 4 and the cosine of phi minus 1, and we take the magnitude. And now what we'll see is that whenever phi is equal to 0, we'll get cosine of phi is unity, and therefore this is going to be 0, and we'll have the cosine of that is pi by 4. Is it correct really? It's 0 multiplied by 0. What do we get? That is 1 minus that. So this is going to be 0, and we have that equal to unity. Yeah, that's correct. So it will be cosine of 0. So we have unity. And if it's pi, that is, if phi is 0 or phi, we'll get a value of, if phi is equal to pi, we have that is going to be minus pi, and that therefore minus 1, and therefore we have 2, and therefore we get minus pi by 2, and therefore cosine of 90 degrees is going to be 0. So this we see is a different kind of radiation it's now going to be maximum along the direction of the axis, along the axis of the array, and it's 0 in the directions opposite these values. And hence, the radiation is along the axis of the array, and we call this the end fire pattern, and has a cardioid structure. That is, backwards, in the backward direction, we have 0 radiation, but in the forward direction, that is, we have radiation, so to speak. And the cardioid is such that we'll have a null coming in the backward direction, and we shall show how the picture looks like. So the reason behind this kind of structure is because the pi/2 phase lag in the excitation of the element 1 will cancel the time lead in the arrival of the waveform from element 1 in the theta equal to 0 degrees direction relative to element 1. What does that mean? We know that the element 1 physically is closer to the element, or to the field point, than element 1, that is the element 0. And therefore, its field will arrive there earlier than the radiation from the element 1. But we are exciting that current, that element, with a current that is delayed, and therefore its field is delayed by the same amount as the other one, and therefore this cancels that radiation lead. So the cardioid figure is as shown there. So we'll have a broad kind of value, and therefore this is more like, say for example, you are dealing with a ship that has guns that are placed in the starboard, so to speak, and therefore you'll have to orient your ship normal to the coastline for you to shoot your cannons into the coast, so to speak. And that's why we are calling it an end fire kind of array pattern. So example, a linear array is formed by 3 isotropic point sources spaced λ/2 apart and excited by in-phase currents of magnitudes in the ratio 1 to 2 to 1. Determine the radiation field distribution of the array. What we notice here now is that we are not exciting the antenna array elements with the same current, but the ratio in the amplitude is in that form, more like what you call the Pascal triangle when you recall your mathematics. So this array, we can always treat it as 2-element arrays, okay? A 2-element array formed by elements that are themselves 2-element arrays of point sources, all spaced at λ/2 apart and excited by in-phase currents with equal amplitude as shown. That is, we'll have the first antenna here with a current, say, of normalized current of unity, the second element there with a current of 2, okay, normalized current of 2, and that one is the third element with a current amplitude of unity, okay, normalized, and they are all spaced λ/2. And therefore, how we can deal with it is that we have the first antenna, that is the first array like we have already solved, and then we have the second array where we have co-located the two element arrays in that form, and therefore we have λ/2 on that side and λ/that. And this is usually referred to as a binomial array because of the feeding in the ratio 1 to 2 to 1. You could get, for more values, you can get 1, 3, whatever, and so forth. That is, you add that and you get the value, okay, for the arrays, so to speak. So the element factor of this equivalent array will therefore be the array factor determined as before. So instead of using the cosine, say for the f of theta is just going to be the same as the first element, 2-element array will have a array factor of cosine pi/2 cos phi, And the array factor of the equivalent array, now having two elements of this nature, will have the same value, so that the principle of pattern multiplication, the radiated field, will have a form of the cosine of pi by 2 and the cosine of phi all squared. And this gives us another value of 4 times. That is, we are multiplying that value with the other value. So the 3-element broadside array with non-uniform excitation is a special case of a family of arrays that are called binomial arrays and that do not exhibit any side lobes. So now we are going to specialize this now to a larger value, that is where we have n elements, okay, all excited in a binomial way. Okay, that is a binomial array excited with equiphase currents with amplitudes in that ratio. That is the combinational ratio. That is where n is equal to 0, 1, 2, and so forth. So you know how this one comes is the n factorial or n minus whatever factorials and so forth to expand that value. So for the two to be, for there to be no side lobes, the element spacing must be always lambda by 2. And the main lobe will be broader than for an identical array that has been excited with equi-amplitude and equi-phase currents. So therefore, the binomial the binomial array will have lower directivity, but has the advantage that there is no radiated power leakage to the side lobes. So for a general linear arrays, the arrays will have identical elements equally spaced along the x-axis or the axis of the array. And we consider such an array with an n element and driven with equal amplitude currents of uniform progressive phase shift along the line. So the array pattern function is then going to be the product of the element and the array factors for the individual elements in the multiplication principle. And with the array axis along the x-axis by assumption, the normalized array factor in the xy plane will therefore be given by A of psi equal to the sum, okay, over the number of elements that we have, multiplied by that phase shift factor and divided by the total length or the total number of elements. And this, when we use the additions of power series or the geometric series, we get a value of 1 minus exponent of j n by psi over 1 minus exponent of j psi 1. And I'm sure you remember this equation or this expression from your signal processing, where we get this is the sinc function. That is the sine n plus psi by 2 or sine psi by 2 there, where the psi is defined as before, where that is the kd multiplied by the cosine of phi plus the phase delay or the phase angle of the currents. And thus, we can get the magnitude of the array pattern, and we get 1 over n sine n psi by 2 over sine psi by 2 on magnitude. So the radiation pattern will therefore depend on phi and the electric length kd, as well as the phase of the current or the excitation current alpha. And as phi varies from 0 to pi, then psi will vary from kd plus alpha to minus kd plus alpha. And hence, it will cover a range of 2 kd equal to 4 pi multiplied by d divided by the wavelength of the signal. And this range is therefore usually called the visible range of the radiation pattern. For those of us who are attentive in the in the ECT, I think in third year, when you are designing filters using the S-plane, this is the same kind of thing we dealt with. And therefore, this lends that whatever useful in the design of arrays, antenna arrays as well. So we note the following. The array pattern is going to be maximum whenever psi is equal to 0, or in other words, kd cos theta naught of phi naught plus alpha is equal to 0, where phi naught is, of course, the given value of phi where the psi is equal to 0. And this will be given by the cosine of phi naught equals to the minus of alpha by kd. And the main lobe will be broadside if phi naught is equal to plus or minus 90 degrees, or rather alpha is equal to 0. And the array is excited by in-phase currents. That's that there is no phase delay in the currents. It will be it will be end fire if we have phi naught equal to 0, that is alpha is equal to the minus of kd. So the array factor is 0 or has a null whenever that argument in the magnitude definition n phi by 2 is equal to plus or minus n pi, where n is an integer. So the null locations of phi are therefore different in broadside and end fire cases because of the different type excitations. That is where we have alpha equal to 0 and alpha equals to minus kd. So suppose psi at 0, 1 is the value of psi at which a psi attains its first nulls. That is why it becomes 0.
Excuse me, sir.
Yes?
I'm afraid our time is up.
It's up. You're going to another class. I had only about 10 slides to go, but anyway, we can stop at that point. We can talk about that tomorrow. So what do you want? What do you suggest?
There was a question in the chat.
So then I'll look at the question, then answer that question, then we can deal with that tomorrow. And that's page 25. So what is the question? Usually it's good to ask the question by using, using the microphone, because when I'm speaking, it's very difficult for me to see the chat screen, because it takes up all my screen. That is, the slides take up all my screen. So for expression with time variant, what is this time variant? What nominal value does one choose when time hasn't been stated? I don't understand this question. The question is not specific on today's lecture. Expression with time variant. Could you please elaborate what it is you are asking here? Because I don't know whether you are asking for, in what relation, in what context? Mutisia. He asks the question and disappears. So, okay, I'll look at it next time when guy comes back. So since you are going to another class, then I'll stop there and remind me about the question.
Okay, thank you.
I don't. Yes?
We were requesting, in case the situation in the country does not change, if it was possible to have our CAT on the week of 11th May to 17th May.
Is that not when you are supposed to be sitting exams?
Will it also be online in case?
Oh, those ones are not going to be online. I think the university burnt its fingers with you guys last time. Yeah, whatever the way that the exams were done was not very nice. Very okay. So this question I'll have to check. You have to be more specific. I look at what that chapter 3 you are talking about. The time, if you are dealing with sinusoidal or whatever, or time harmonic time dependent fields, you don't have to put the time in there all the time. You can always work with it, because most of the Maxwell's equations are special derivatives, and any time derivative can be replaced by the j omega. And therefore we'll put in the time issue when you are asked for the instantaneous values. I hope that one answers you. But sometimes you can be asked to show a given distribution at a given time. So you choose a time that is convenient for you. Say, for example, time equal to, t equal to 0. The same thing happens with a space. You don't go looking for a z plane that is different from 0. You want to look for a z plane that is, it will give you a nice kind of thing, a nice kind of expression without those phase factors and the likes. Okay, and that's why we always choose z equal to 0 or t equal to 0 when we are trying to draw the whatever the given values or the given distribution functions. I hope that answers you. If it doesn't, let's talk about it tomorrow. Okay, good day, and have a nice day. I'll think about that CAT thing. I don't know whether I'll be allowed to give CAT online, so I'll have to find out with the chairman first before I can give you a definite answer. I hope that answers you, Bogori.
Okay. It does. Good day.
Okay, good day. Bye.